This is the final video in the EDEXCEL P3 revision tutorial series. Today we will be looking at kinetic theory and gases. We will look at the link between kinetic energy, temperature and pressure. In today's video we will look at the term absolute zero in terms to particle movement. We will look at calculating gas volumes at fixed mass and pressure at different temperatures, and then we will look at carrying out calculations for varying gas volume, pressures or temperatures. In order to understand kinetic theory, we must first understand particle diagrams. We need to be able to draw these for solids, liquids and gases. As you may remember, here are our particle diagrams. We have our solids, where you have strong forces of attraction which hold all of the particles very close together in a fixed shape. The particles do not have much energy and as such will only vibrate around their fixed position. Our next particle diagram is for liquids. In our liquids, the forces of attraction between the particles are weaker. This means that the particles can flow over each other, in that they are close together but can move past each other. They have more energy than the particles in a solid and can move in random directions but at low speed. Finally, we have our particle diagram for our gases, where there are almost no forces of attraction between the particles. You have very, very little force between them. However, they have much more energy than those in both liquids and solids and are free to move around. As such, they will travel in random directions at high speeds. Now that we have looked at the particle diagrams, we can ask, how is gas pressure caused? Well, gas pressure occurs when gas particles hit the edge of the container they are stored in. The force of them hitting the edge of the container is what we know as gas pressure. So, how can we affect gas pressure? Well, a simple way of affecting gas pressure is to decrease the size. So if we have a certain number of particles in a specific volume and we simply decrease the volume, the pressure will be more, as there will be more collisions of the gas particles with the edge of the container. It's important to note that most of the space taken up in the container is of empty space, as the particles are incredibly small. However, we can also affect the pressure by looking at temperature. So, what is the relationship between pressure and temperature in gases? Well, simply, when we increase the temperature, the pressure increases. This happens because the gas particles have more energy and therefore can move faster. Likewise, when we decrease the pressure, the temperature reduces. This happens until we reach something called absolute zero. This absolute zero temperature is also known as the zero pressure temperature and is calculated at -273 degrees Celsius. We can see that as we reduce the temperature, the pressure will eventually reach zero. This is because the particles will have no kinetic energy and therefore will not be able to exert a pressure onto the side of the container. This temperature of -273 degrees C is known as 0 Kelvin. Actually, the temperature is -273.7 degrees C, but scientists tend to ignore the 0.7 in calculations, as do EDEXCEL in the mark schemes. This temperature is known as an absolute zero. So absolute temperature is measured in Kelvin, and it represents the temperature at which particles have zero kinetic energy. It goes up in the same steps as degrees C. For example, the freezing point of water is 273 Kelvin, whereas the boiling point of water is 373 Kelvin. In the exams, you can be asked to calculate Kelvin from Celsius and will need to in order to carry out gas equations. In order to do so, if you're converting from degrees Celsius to Kelvin, then simply add 273, and to convert from Kelvin to degrees Celsius, just subtract 273. It is also important to note that when you are writing a temperature in Kelvin, you do not use the degrees sign like you would for Celsius or for Fahrenheit. By using temperature in Kelvin, we are able to compare it to kinetic energy in order to calculate the volume taken up at a constant pressure by a gas. If we compare the kinetic energy and temperature in Kelvin of gases, we can put together the following graph. We can see that as we increase our temperature in Kelvin, the kinetic energy of our particles increases. This means that the Kelvin temperature of a gas is directly proportional to the average kinetic energy of its particles. This means that if we were to double the temperature in kelvins, then we would double the average kinetic energy of the particles. As the pressure of a gas depends on how fast the particles are going and how often they hit the walls, this means that when a gas is at constant pressure, its volume will be proportional to its temperature. This relationship is known as Charles's law. Charles's law states for a constant mass of gas at fixed pressure, the volume occupied by the gas is proportional to its absolute temperature. What this actually means is that if you have a gas and heat it up, you give the particles more kinetic energy so they move around faster. The gas will expand to take up more room, and hence the volume increases. So the Kelvin temperature of a gas is directly proportional to the average kinetic energy of its particle. This means that we can put together the following equation. Here is our equation. So we have volume 1 equals volume 2 times temperature 1 over temperature 2. What this means is that the volume at the beginning will be equal to the volume at the end times by the temperature at the beginning over the temperature at the end. The 1s signify that this is before the change, and the 2s are after the change has taken place. We will now look at an exam style question. So a gas is heated from a temperature of 290 K to 315 K. Assuming the gas is at a constant pressure, find the initial volume of the gas if the final volume is 95 centimeters cubed. We are given all of the information we need in the question. We simply need to work out which bit is which. When we read through the question, we are told that we need to calculate the initial volume. This will be our volume 1. And we are also told that the final volume is 95 centimeters cubed. This is our end volume, our volume 2. We are also given both of the temperatures that we need. First of all, we are given the initial temperature of 290 K. We can tell this as the question states that the gas has been heated from this temperature. This is our temperature 1. And then finally, we are also given our new temperature of 315 K, which is our temperature 2. We now have everything we need in order to calculate V1, so we will simply do 95 times 290 divided by 315, giving us an answer of 87.46 centimeters cubed to 2 decimal places. It is important to note that you do get given this equation on the front of the EDEXCEL P3 paper. I will now provide you with 2 additional questions to practice this. You could now pause the video to calculate the answers to these 2 questions. So for question 1, you were asked to work out the new volume, that is volume 2, from the original temperature, the new temperature, and the original volume. That gives you the following equation. So we have our 2 meters cubed equals our unknown, our volume 2, times 200, which is our original temperature, our T1, divided by 300, our new temperature. We then need to rearrange this. In order to do this, we are going to times both sides by 300 and then divide both sides by 200, giving us the following new equation. So we now have our volume 2 as our subject of the equation, 2 times 300 over 200, giving us an answer of V2 equaling 3 meters cubed. In our second question, we are given a different gas, again at a constant pressure, which is being compressed from 20 litres to 15 litres. This gives us our volumes. As it is being compressed, our first volume is 20, our second volume is 15. It also tells us that the new temperature is 275 Kelvin, so we are looking for T1, which will give us 20 litres equals 15 litres times our unknown temperature over 275 Kelvin. When we rearrange this to make T1 our focus of the equation, we will end up with 20 litres times 275 Kelvin over 15 litres, giving us an answer of 366.67 Kelvin to 2 decimal places. So far, we have looked at the relationship between temperature and volume, which change when the pressure is kept the same. However, what happens if we change our pressure? Well, an easy way to do this is to decrease the volume. If we decrease the volume of the container, the gas particles should collide with the sides of the container more often, therefore the pressure increases. This enables us to look at another relationship, this time the relationship between pressure and volume if temperature is kept constant. This is known as Boyle's law. This relationship between pressure and volume is inversely proportional. This means that if the volume goes up, the pressure will go down, or vice versa. Because of this, we can use the following equation. The equation for working out the pressure and volume, we can use this equation. So we are now looking at P1 times V1 equals P2 times V2, where the 1s and the 2s are the initial and the final, the before and after, P for pressure and V for volume. So if a gas has a volume of 3 meters cubed at a pressure of 20 newtons per meter squared, what will the pressure be if the volume is reduced to 1.5 meters cubed? In this question, we have been given the initial volume, which is given to us at 3 meters cubed, as well as our initial pressure of 20 newtons per meters cubed. We have also been asked to work out our new pressure. This will be our P2, our unknown, and then finally we have been given our new volume, which is our 1.5 meters cubed. In order to calculate our new pressure, we need to divide both sides by our second volume, our 1.5 meters cubed, giving us P2, our unknown, equals 3 times 20 over 1.5, which gives us an answer of 40 newtons per meter squared. We have now looked at 2 of the 3 equations that you need to know for kinetic energy and gases. We can now combine them together in order to give us the gas equation. In this video tutorial, we have looked at 3 laws. The first of these, the pressure law, stated that pressure is proportional to temperature. We then looked at Charles's law, which stated that volume is proportional to temperature. And then finally, we looked at Boyle's law, which stated that pressure and volume were inversely proportional. With these three laws, we can then work out something known as the gas equation. So we can combine the equations we previously looked at into one final equation, where we can state that pressure times volume divided by temperature is equal to our constant. This can then be further applied to an equation to give us the following, where we have P1 times V1 over T1 equals P2 times V2 over T2, where our P is our pressure, our V is our volume, and our T is our temperature, ones being our initial or before the change, and then our twos being after the change or our final pressures, volumes, and temperatures. We will now look at some example questions using this equation. Here are some example questions using the gas equation. The gas equation is up here for reference. I will go through this first question here before allowing you time to go through the second two questions. So, our first question, we have an ideal gas. This means it will follow the gas pressure law, has a volume of 2 meters cubed and a pressure of 101 kilopascals, which is equal to 101,000 newtons per meter squared at a temperature of 300 K. This gives us everything we need for the first half of the equation. We have got our initial volume, which is 2 meters cubed. We have also been given our initial pressure of 101 kilopascals. It's asking for the answer in kilopascals, so we will keep it in that. That is our initial pressure, our P1. And finally, we have also been given our initial temperature of 300 Kelvin. For our values at the end, we have also been given our new temperature, which is given to us as 400 Kelvin, and we have been told that it has been kept at a constant volume. So the constant volume, we have our volume previously, this will be V2. We have been asked to calculate our new pressure, so finally this will be our P2. From this, we can straight away work out our answer to our left-hand side of the equation. We will do 2 times 101 divided by 300, which gives us an answer of 0.673 recurring. If you were to calculate this using the 101,000 newtons per meter squared, this would give you an answer of 673.3 recurring. Both answers would be correct, providing that your final pressure is given in kilopascals. We can now simply rearrange the equation by timesing both sides by our 400 Kelvin and dividing both sides by our 2 meters cubed. This gives us a value of 134.6 kilopascals. If you have been working with the 101,000 newtons per meter squared, you will have an answer of 134,666.6 recurring. In order to put this to the nearest kilopascal, we need to round this up to 135 kilopascals. In the second question, it is looking at the same gas as question 1, so you need to use the same starting volume and that the pressure is being kept the same. This time the temperature is going down from 300 to 200 Kelvin. If you would like to pause the video in order to calculate the answer to this question. This will give us a new pressure of 67.3 kilopascals, so 67 kilopascals to the nearest kilopascal. Finally, in question 3, we are now looking at a different gas, this time being kept at 300 Kelvin, that's its initial temperature, and a pressure of 101 kilopascals, which is allowed to halve in volume while being kept at the same pressure. We are looking for the new temperature. In order to do this, we do not need to know the exact volumes, only that the second volume must be half of the first volume. In order to do this, simply make the initial volume 2 and the finishing volume 1. Therefore, the volume has halved. We will now look for the new temperature. Please pause the video and calculate the new temperature. This gives us a finishing temperature of 150 Kelvin. We will now link these ideas of gas pressure and gas equations into medical physics, as we have throughout the duration of P3. We can also use these principles of gas pressure in medicine in order to produce bottled gas canisters. The gas inside is kept at a much higher pressure than the atmospheric pressure. The atmospheric pressure will be 1 atmosphere at sea level and decrease as you move higher up away from sea level. This allows us to store high volumes of gas in a small space. The difference in pressure between the inside and outside of a gas bottle is what causes the gas to flow. When the pressures are equal, the gas has no reason to go anywhere, so won't flow. Once this pressure inside and outside of the canister is equal, this means that the gas will no longer flow out of the canister, meaning that you will end up with a canister with a volume of gas in it equal to the volume of the canister. As the gas is kept at very, very high pressure, gas canisters need to be made of materials that are strong enough to hold gases under these high pressures without buckling or splitting. For example, steel or carbon reinforced aluminium. The size, materials and pressures used in gas canisters depend on where and what they're used for. For example, on an ambulance where space is limited, small canisters store gases at very high pressures in order to maximise the amount of gas they hold, but minimise the amount of space they take up. One potential exam style question can be seen on the next slide. So an exam style question might be as follows. A 2000 centimetre cubed bottle of oxygen is stored at a pressure of 4 atmospheres. The pressure outside the bottle is 1 atmosphere. What volume of oxygen is released into the atmosphere if the bottle is opened? Assume that temperature is constant. As we are assuming that temperature is constant, we will be using Boyle's law. So we'll be using the equation V1 times P1 equals V2 times P2. So in the question, we have been given our initial volume. This is our 2000 centimetres cubed. We have also been given our initial pressure, our 4 atmospheres, our P1, and then finally we have our P2, our secondary pressure of 1 atmosphere. So when we rearrange the equation, we will get V2 equals V1 times P1 divided by P2. When we plug our numbers in, we will get the following. 2000 times 4 divided by 1 is equal to V2. So V2 is equal to 8000. However, as we are looking at gas escaping from a bottle, we must also take into account that once the pressure inside and outside of the container are equal, then no more gas will escape from the container. This means that our 2000 centimetres cubed will remain inside of the container. In order to work out the volume of released gas, we must take our answer for V2, our 8000, and take away our 2000 centimetres cubed of gas that will remain inside the bottle, giving us a released volume of 6000 centimetres cubed. This concludes this series of revision tutorials on EDEXCEL P3.